Welcome everyone to the seminar. I'm Tony Roskilly. I'm a Professor of Energy Systems at Durham University, and I lead the EPSRC Network Plus on hydrogen fuel transportation. So this event is organized by the Network H2, and it's part of a series of webinars looking at different aspects of hydrogen research and development in the transportation sector. This week, we're welcoming two speakers that will present findings from two projects that the network actually funded and instigated. Let me introduce our first speaker today. It's Dr. Stuart Hillmanson. He's a reader in railway traction systems and is within the Department of Electrical and Systems Engineering at the University of Birmingham. And he leads on railway traction systems in the group there. His main area of research is in hybrid traction systems for use in railway vehicles. He's a member of the Birmingham Centre for Railway Research and Education, and he's had a large number of research projects in this area funded by the EU, EPSRC, Network Rail, and industry and DFT, etc. He's going to present to us on the project, which is impact of hydrogen standards on the UK transportation system. So over to you, Stuart.
Thank you very much, Tony, and hopefully everyone can see my opening slide there. We actually are still conducting this small project in partnership with TRL. We've got a couple more weeks just to pull everything together and finish everything off. So, the team that we have doing this is a partnership between TRL, Transport Research Laboratory, and ourselves at the University of Birmingham. They're the name of the people involved in the project, and a colleague, Dr. Julie Ma, Assistant Professor at Durham University. So we came together to put the proposal in to tackle this important project, which is about understanding the standards landscape for hydrogen rail vehicles and identifying gaps, problems, issues, showstoppers, and what the community needs to focus on as this technology is introduced into the rail sector. And this, I think, is motivated by the fact that my group at Birmingham had developed, in partnership with Porter, the first hydrogen mainline train. And we've done that in the absence of any rail specific standards. And I think it's always important that we make sure, as the technology develops, the standards develop, and to make sure that the technology is introduced effectively and at appropriate cost, and we don't create problems for ourselves by having conflict in standards and so on and so forth. So yeah, this is a project overview to undertake that research into identifying safety standards and regulations required for safe use of hydrogen in the rail sector. And obviously we're grateful for the funding from Durham and the Engineering and Physical Sciences Research Council to undertake this work. And the outputs, which are nearly there now, about producing high level safety requirements and identifying particularly barriers and issues surrounding the sort of introduction of and safe operation of hydrogen in rail. And as I said in my introduction, yesterday we had a really good workshop. We got some really good stakeholders present, and we're just sort of digesting the outputs from that at the moment with our partners at TRL. There's going to be some key findings from that will help shape the future of hydrogen rail and community that are undertaking the development of the technology. So why have we got hydrogen in railways? I say this pretty much every time I talk about hydrogen in railways. The best way of delivering power to a rail vehicle is actually through electrification. So if you have high density, high power operation, then it's pretty much no brainer to electrify that route. And railways are very good at densely packed services. If you just have to look at something like the Elizabeth line, which just opened in London, that's obviously a 25 kV electrified railway, and that was an obvious choice for that. However, if you look at the whole railway system, it's a sprawling system, and lots of the network just simply don't justify the economic cost of electrification. And in the medium term and long term, we need to get a solution that will provide autonomous traction power for those vehicles. And pretty much there's an emerging consensus that hydrogen is a strong contender to provide traction power for these types of vehicles. And there's examples in Germany with the Coradia, Island, Alstom's train, and the Hydroflex in the UK, which has now been further developed by Porterbrook and is pretty much ready for passenger operation. So we've kind of got the trains, and they were developed within the existing standards, but there are specific railway issues that then rear their ugly head and cause problems in terms of introduction of this kind of technology. This picture was taken by drone, actually, but University of Birmingham organised this mainline testing of the Hydroflex train back in 2020. I think we took the train out onto the main line. So this is an existing train that we re-engineered to have a fuel cell and battery system on board, providing traction power into it. And I think we did about 75 miles in total over 3 occasions, where we proved that train could operate on the mainline network and operate successfully and not interfere with other rail services or interfere with other systems on the rail network. So we went through a process to get that approved. This train's just running over Stratford, a river just south of Birmingham, River Avon, and it's heading towards Evesham on the left of the picture. And it's an electric train running on a non-electrified network. Still has its pantograph and performs. And the passenger experience is very much like what you'd get on an electric train. So no noisy diesel engines and quite a pleasant environment for the passengers. Just a little bit of background. I'm going to spend some time talking about Hydroflex and particularly talking about the methods we use to prove its safety and how we did that. And then I'll talk about some of the work that we've done looking at the standards and identifying the issue going forward. So Hydroflex was launched at Intertrans in 2018. That's when we kind of hit the go button to do this. And that was in September. And then the following June, we had the train ready to run at an event called Rail Live. So that was in 2019. That event, Rail Live, is actually happening next week. So we've got Rail Live 2022 happening just next week, if anyone's interested. So yeah, it was developed and showcased at Rail Live in 2019 in just 9 months, and then after that we got funding from Innovate UK to take it onto the main line. So we took what we did. And at all points, we'd always anticipated taking the train onto the main line. So much of the engineering work was done with the relevant mainline standards in mind. And we got it certified by 2020 to take it onto the main line. And that was the picture you saw, the train going over the bridge on the River Avon. Here's some pictures of the first version of Hydroflex. So the version, if you were to go to Rail Live next week, you wouldn't see this train. You see the next version of it, which is based on a different actual train, but it's the same class of train. So the donor unit was a class 319. It done about 2.5 million miles in its lifetime and been retired. So it spent its life going between Bedford and Brighton, and was retired then in 2017. And it was sent to Long Marston storage site, the one that's operated by Porterbrook. The reason we chose this was because it already had existing electric traction system on board, so could take power from 25 kV or the third rail system. And the reason why we wanted to do this rather than a diesel train is because it had electric, traction motors on it, rather than, diesel trains have hydraulic drive, and we would need a lot more engineering work to convert a diesel train to hydrogen than an electric train to hydrogen. So most of the work was focused around interfacing a new battery and fuel cell system into the power system on the train, and to get the train to accept power from an unexpected source. So we actually interfaced through the guide rectifier from the secondary part of the transformer. So we made use of those diodes to partly protect our battery and fuel cell. This is a picture, a sort of cutaway of the vehicle that had all the equipment in it. So as part of the first trials, we stripped out the seats from this second vehicle to the left, the MSO, so it stands for Motor Standard Only. Stripped all the seats out, put our equipment in there. As I said, this was a nine month project, and we needed to do it quickly. So there wasn't possibility of packaging everything underneath the train, which is probably what you would want to do with at least some of the equipment for a full scale implementation of this. The big advantage of this arrangement, and I think the most powerful one, rather than it being easy engineering, which was convenient, was the fact that we were able to showcase the technology. And I think several thousand people probably had an opportunity over the Rail Live event and other events to come and stand in the carriage when the train wasn't moving and get a tour of the equipment, and for people to see a fuel cell and hydrogen tanks up close. These are new technologies that people aren't familiar with, so I think it was really good for us to be able to demonstrate, yeah, this is a fuel cell. You get hydrogen pipe goes into this part, and then these two big cables on the outside of it take away DC power away from it, and so on. And certainly for them to see, I think what was quite impressive was the engineering that goes into things like the hydrogen storage system, which was provided by Luxfer. It's a truly outstanding piece of kit. So this slide shows some of the pictures midway through the installation. So the one on the left shows the floor of the train with all the seats removed, and you can see cutouts where on the floor, those black kind of bars where there are places to attach items to. So they would be expected to have seats attached to them. So obviously seats on a train have to be securely fastened. So they're actually a very strong part of the train. So there's a first standards then. The standards that we needed to meet was this GMR 2100, which is the structural integrity standard for the vehicle. And on the right hand side, you can see a picture of a battery frame and a battery raft being installed onto the floor of the train. So the batteries, as they came delivered, weren't in the housing that they were provided with. It wasn't structurally sound in terms of meeting that standard. So we needed to build a frame around the batteries in order to house them to meet that structural integrity standard. So, for example, that gives certain fatigue load input to the assembly and impact loads and so on. So if the train had a heavy shunt or something like that, there would be like a longitudinal acceleration, and we need to make sure that all the equipment stayed in place if such an event would happen. Of course, during operation, nothing like that did happen, and the actual vibration and G environment that you get inside a train when it's running properly is really tiny. So you could say it's over-engineered, but it's engineered to cope with those extreme and rare occurrences. So a picture of our tanks from Luxfer. So this is one of the issues with hydrogen trains, is the tanks are pretty big. So they store 5 kilograms each, and we had 4 of them. So we had 20 kilograms of hydrogen. A real train, we'd be looking to have between 200 or 300 kilograms of hydrogen stored on it to give it a decent range for a day's use. Again, another standard here that we used was EC79, which is a European standard developed for mobile applications of hydrogen, and we used that as our basis for how to construct and install this within the vehicle. And this is technology adopted and developed for the automotive sector. Here's a picture of the fuel cell, 100 kilowatt HD7 Ballard fuel cell that we got supplied by Ballard, but we built all the controllers for it at the university through CAN bus and so on. And then we had a lithium-ion battery pack supplied by Denchi. There were two strings of 12 modules, giving us a voltage of 625, which was the system voltage for the train. I should say the one thing to point out here is a fuel cell hydrogen train is inevitably going to have a battery on it, and introducing batteries into trains is probably as complicated, if not more complicated, than introducing a hydrogen system. So both need probably as much attention as each other in terms of understanding safety, because these are new things for rail vehicles as well. Something that's often forgotten is the refueling. So, filling the train with hydrogen, and the way we did it when the train was on mainline testing was by buying high purity BOC hydrogen, decanting it into this fuel cell systems truck, which pumped it up to a higher pressure, and then that would be decanted into the train. And we could refuel the train in about 10 or 15 minutes, but probably could do it faster. This side of the whole standards piece around logistics and refueling is something that we've discovered needs further attention and further investigation as part of this project, and that's something I think will be one of the outputs is a recommendation to make sure all that's coordinated properly, particularly in terms of where depots are sited, how we handle hydrogen in a depot environment, and how we handle hydrogen in depots environments with existing other fuels like electrification and diesel. Anyway, we took it onto the main line, and this is the method, the safety approval method we used for that. We used something called Common Safety Method, which is a European-derived directive on understanding how to introduce new technology into the rail industry, which is the methodology that rail undertakings use to get anything approved to run on a rail network. And then we have an independent assessment through an accredited body. The Office of Road and Rail were also involved in this. They accepted the technical approach for doing this safety work. And then some of the activities in safety involved hazard identification, where you go through line by line every single item of engineering, every engineering change we put on the train. We kind of brainstorm and go, what would happen if that went wrong, and can we mitigate against it, and so on. And that ended up with producing huge amounts of documentation that was tracked back to the hazards to make sure that they were all mitigated properly, and so on. So it's a very big and expensive process to go through that, but it's the same way as other things are done in the industry anyway. And then after that, there's a test station statement against 11 different technical standards was required. There's a few listed there. I've already mentioned GMR 2100, and then things like EMC, electromagnetic compatibility, vehicle maintenance. The operator of the train was Railway Operations Group, and they needed to make changes to their safety management system and get all ORR authorization. And then once that's done and everyone's happy, then you also have to work with Network Rail to make sure the train will be compatible with the network, and that includes EMC. So making sure the train fits down the particular route that you want to run it on, and so on. And then there's things like statements of vehicle configuration. We re-registered the unit as 799001. So the next train that you'd see at Rail Life would be 799002. And then, ultimately it's about convincing all stakeholders that the train is safe. So Porterbrook were pretty much system integrator for this and brought everyone together, including us at the university, to go through that process. And as I said, it was quite a mammoth task that involved quite a lot of engineering hours to do this. Example of EMC testing pictures. So the train already had an EMC kind of footprint, and we had to make sure and prove that we didn't move any of the electromagnetic radiation outside of that. So things to make sure we don't affect train detection and signaling compatibility. AWS's automatic warning system or train protection and warning system immunity. These are safety critical features of the railway, and it's absolutely essential that you make sure the rail vehicle doesn't interfere with that. And then things like human exposure. So there were additional cabling carrying quite high currents, so to make sure that any new magnetic fields weren't problematic, so on and so forth. We did all that without any specific hydrogen-related rail standards. So these projects are going faster than the standards. However, hydrogen is not new. It's been used in other industries for some time. There's good standards related to it, and we can use them and adopt them almost straight away. So we had a look at what the standards landscape was, and we produced, and it was possible for me to share this. The picture on the right is a screenshot from a website that we've developed, where you can kind of drill down into the different standards. So, and we divided them up into things like refueling, rail vehicle approval, hydrogen systems, onboard equipment, fire safety, hybrid, and so on. I think one of the things we realised is refueling and depot arrangements probably the most complex part of operating the train, and doing it in a safe and controlled manner is critical. And there's some information there about the various standards that we needed to work with, and there's literally several hundred standards that are relevant. as I said earlier, vehicle approval is the bit that everyone kind of focus on, thinks the most challenging thing, and rightly so, but it's not at the expense of not giving attention to the logistical and depot arrangements. And then these existing hydrogen standards, hydrogen's been used in other sectors. Those are obviously important then to bring those in and to make sure that they're compatible with the railway environment. So this is where issues can arise, because if hydrogen equipment has been expecting to operate in a certain vibration and loading environment as defined in these other standards, and if that wasn't able to meet the railway standards, then we could have a problem, because we'd have to make new or get suppliers to supply different types of equipment that met railway standards as well as these ones. And then there's other supporting systems like onboard equipment, safety, and running the training, hybrid and bi-mode configuration, and so on. So that's a kind of a review of the standards, and we presented that and then that fed into a workshop. And this is, I'm not expecting you to read this, so it's just a screenshot of everything we captured yesterday. So we had, I think, 28 people or something involved in a workshop, when we then posed some questions about looking at the standards landscape, what was missing, what are the things we need to focus on, and we're very much still digesting that, and we're going to go through that. We're very pleased with the interaction that we've got, and we've got a very clear kind of pathway forward to capitalize on this and take the work forward, and ultimately make sure we can introduce this technology in the most painless and safe way as possible. So that was yesterday. So the sort of thing, I think, for me, the immediate things to come out of it is actually probably forming a network of people that are active in the standards area. So there's a standard 63341 that's been developed, a suite of standards that are specific to rail and fuel cell and hydrogen applications. And then another one, a working group on refueling. So obviously the people on the standards committee are busy drafting those, but there's a broader community outside that probably need to work together to make sure we're all heading in the same direction, and respectful of commercial kind of competitiveness that people might have in terms of developing technologies. And then the other big area is identifying critical issues for the railway system which may hinder deployment, so like operation in tunnels. A kind of an easy way of thinking about hydrogen that I'm using to describe it in recent weeks is that if you do stuff outdoors in well ventilated areas, it's a lot easier than if you start operating hydrogen vehicles in confined spaces. And the railway is a mixture of two, so we need to be careful about how we handle it. So I'm sorry if I've gone a bit over time, but thank you very much for your attention.